So everyone sees my screen, right? Great. So today I'm going to talk about Hamilton cycles. It's a bit similar to Euler tours, Euler trials, but I feel it's more important than Euler tours and Euler cycles, Euler trials, because I'm working in some problems relating to Hamilton cycles. I see more research papers on this direction. There are a lot of questions still unsolved. So given a graph G, we are going to ask the following question. We ask if there exists a cycle, this time a cycle, which covers every vertex. So by definition, the difference here with the Euler tour, Euler trial is that we are not allow we do not allow vertices repeated. Okay, so by definition, a cycle do not repeat vertices. So is that vertices are not repeated. So if it happens, if in fact this is a definition, if G admits such a cycle, we call G Hamiltonian. Hamiltonian. Okay, so such a cycle is called Hamilton cycles, and such a cycle is called a Hamilton cycle. If you reorganize all the vertices, it's just exactly like this. We put V1 and V2 and so on, V3, and then we see Vn and we come back. We list all the vertices and we see a cycle. Of course, the whole graph we see some other edges, but if we reorganize it, we see a cycle. So is it possible to find a cycle which you kind of go through every vertex? So for example, if you have an actual cycle like this, and with some pairs, I think it's very clear that this graph does not have, I define this graph like this. My graph is a cycle with some pairs, you see. This graph obviously does not contain any cycle which contain every vertex. Okay, so the main question is what kind of conditions can ensure a graph is Hamiltonian, or what kind of conditions, or even stronger, can you ask some equivalent characterization for Hamiltonian? But in fact, there are no exact conditions for this. So there are no exact conditions which are equivalent to Hamiltonian. Okay, usually you see a lot of theorems, including the main theorem we will talk today. Usually they give a set of conditions which ensure Hamiltonian. Okay, but only one direction. Okay, so for example, this theorem is kind of famous. Dirac says that suppose if every vertex has degree greater or equal than half of the total vertices, so n over 2, then the graph G has Hamilton cycle. So sometimes I just write HL, okay, Hamilton cycle. Okay, so even stronger, we will prove this, but actually we will going to we are going to prove something even stronger. So this is given by all. Says the following. So G has at least 3 vertices. Okay. Suppose the following. Suppose for any 2 vertices UV, which is not an edge. So for any 2 vertices U and V, such that they do not have an edge, we call non-edge. Okay, for any non-edge UV, degree of U plus degree of V is greater or equal than 10. Then G is Hamiltonian. Okay. Oh, G. Let's. I say some. I say Hamiltonian. Let's not avoid saying this. G admits Hamilton cycles. Okay. So clearly, this theorem implies this theorem because it only the condition is weaker. You see. You only look at non-edges and check that the sum of them is greater or equal than n. The condition of Dirac is stronger. So if this holds true, clearly the condition of all holds true. Then you already have Hamilton cycles. It implies that G has Hamilton cycle. Okay. So the proof is I think it's very beautiful, and it's useful even in modern research activities. So there are a lot of questions, like I said, in this area, and the people always have to remember this proof, kind of variant of this proof, to go even further. So it's not a isolated proof. It's kind of important and very inspiring. Let's prove this theorem of all. So we suppose that for contradiction that the conclusion is not true. That the conclusion is not true. So here in graph theory, there is a major, let's say, method. So you want to use induction. So in other words, okay. So it's kind of a combination of induction and searching for contradiction. So you see, we are looking for a proof using contradictions. Suppose, like I started by saying that, suppose for contradiction the conclusion is not true. It means that we have a certain graph G which satisfies the condition of the theorem and without having any Hamilton cycles. So this is very general, this method. You can use it for prove a lot of things. So in this case, we choose a special example. So this assumption for contradiction means that you are kind of you have a lot of possible examples, at least one. But we do not choose anyone, we choose a special one. So we pick an example. Of course, example meaning it satisfies the condition of the theorem and it does not satisfy the conclusion of the theorem, right? We call this a counterexample. We take an example, we pick example in a certain, so pick example which is in some sense an extreme example. So by being extreme, you can put more conditions for this example. Okay, so in this context, we ask this example to satisfy that by adding any new edge, the graph become Hamiltonian. Okay, so this is kind of important. Is it okay? Is it clear? So you can imagine by my first sentence, I suppose that the conclusion is not true, such that there are examples which satisfy the conditions and does not admit Hamilton cycles. Okay, so I look for example, one non-edge of this example, and I add this edge. There is a possibility that this edge will make my graph Hamiltonian. Okay. But if it does not make my graph Hamiltonian, I take this new graph. I can keep doing this until at some point I cannot put any new edges. So at that point, I fix this example. I call it the extreme example. So this example, again, it satisfies my conditions, and also it has one extra condition. Any new edge will make it become Hamiltonian. Is it okay? So this new kind of property comes for free. So this kind of argument is pretty important. Okay, because you can imagine I cannot do this forever, because eventually I will obtain a complete graph. A complete graph, obviously, it is Hamiltonian. So I have to stop at some point. And when I stop, the graph, one, it satisfies this property. Two, it does not admit Hamiltonian cycles. Three, any new edge, if you add to it, the graph will become Hamiltonian. Okay, so in other words, so I think at this point, why I arrive at this graph, I still call it a G. Okay, I still call this G. Okay, and in G there is, so I just take a non-edge, and because if I add this edge, the graph will become Hamiltonian. It means that there is a path which I write V1, V2, and so on until, for example, n minus 1, Vn. It goes through all the vertices, while and V1, Vn is not an edge. Okay? So, and this path we call this Hamilton path. Okay, we call this Hamilton path. So the graph admits a lot of Hamilton passes, but no Hamilton cycles. So it's a path. It goes through all the vertices, but the starting point, starting vertex, and the ending vertex, there is no edge between them. Okay, now we recall our property assumption that the degree of V1 plus the degree of Vn is greater or equal than n. So, okay, the assumption is that for any non-edge, the degree sum is greater or equal than n. Okay, so we know that in particular, the degree of this guy and the degree of this guy is greater or equal than n. Okay, so we have to prove the following claim. So there is, looking at this picture, so let's say picture A, looking at this picture, looking at the picture A, the claim is that there is a vertex Vi. For example, at some point here, okay, I'll draw this picture again later. So such that V1, Vi plus 1, and Vi, Vn are both edges. So it's basically if the degree of them is too large, there is no room to avoid this situation. So what happening is that we have V1 here, and at some point we see Vi, and here is Vi plus 1, and we have some more vertices here, and this is Vn, something like this, V2. Okay, so I'm saying that V1, Vi plus 1, and Vi to Vn, these are both edges. So the proof of the claim is pretty clear. Okay, so you just count. But okay, to make it very rigorous, so let's suppose the degree of V1 is k. Okay, so in particular, we know that the degree of Vn, it will be greater or equal than n minus k. Okay, because of this. Just I've moved this to other side. This is k, so this is greater or equal than k minus n minus k. Okay, so we will get a contradiction with this. So then we list all of its neighbors. So V2 is its neighbor, right? And then we put V2 equals I1. Okay, so it's just the first neighbor, I1. And the second neighbor, we put I2. Okay, so Vi3 until Vik are its neighbors. So it's nothing mysterious, nothing fancy here. I just because its neighbor could be V2, V3, V4, and so on. Maybe I put it in an increasing order, and I call the first one Vi1, which is V2, because V2 clearly is its neighbor, and the Vi2, Vi3 until Vik. It has exactly k neighbors. So I write this to avoid to be in a very awkward situation to actually drawing it. Okay, so we have k neighbors of neighbors of V1. Okay, right. So if I cannot have this situation, so because you see, when V1 has a neighbor, this guy minus 1, So Vi minus 1, Vi plus 1 is a neighbor of V1. Then Vi, I want to conclude that some Vi will be a neighbor of Vn. If none of this happen, so suppose, again, for contradiction, okay? For contradiction, that this guy, Vi2 minus 1, okay? The vertex before Vi2, Vi3 minus 1, etc. until Vik minus 1. If all these k minus 1 vertices are not neighbors of Vn, okay, suppose for contradiction we have this. We are trying to find one of them to be a neighbor of Vn. If all of them are not neighbors of Vn, then what happens? Then I want to count. I count the possible positions for Vn neighbors. You see, V1 is not a neighbor of Vn. This is the kind of the beginning assumption. If V1 is a neighbor of Vn, we are done. We find the Hamilton cycle. And we have these k minus 1 vertices. They are not Vn neighbor, right? Vn is not a Vn neighbor by himself. So V1, Vn, and these k minus 1 vertices are all not neighbors of Vn. So the number of remaining positions is at most we got n minus 2 minus k minus 1. Okay, so this is n minus k minus 1. Okay, and this implies that the degree of Vn will be smaller or equal than n minus k minus 1 because there are at most of these positions. If I put all these possible positions as neighbor of Vn, then the degree of Vn is at most this number. Could be smaller even. But this is a contradiction with this, you see? I got a contradiction. So this concludes the claim. But in fact, after the claim, the theorem is very clear. So you see something like this. And can you see a cycle here? So this is V1. This is Vi. This is Vi plus 1, and this is Vn. So I got this one. I can actually delete this vertex, this edge, and I continue to move here, and I move here, and I come back. So this is a cycle. Okay. So this is the proof. Any questions? Okay. Are you happy? So this is a kind of a main theorem I require you to know for today. So we will talk about more things, but will be less required. I mean, will be I will not give full details, or it's too difficult, depending on different cases. But this theorem, I think I require you to know. So this is kind of important. You have to remember to use it also. So for example, before I going further, I'll put a problem. Olympiad task here. I think it's an Olympiad context problem. So let me put 6 colors of fabric. Fabric is just I mean, you use it to make clothes. Okay, and we decide to use which are used to make scarves. Okay, scarf is just kind of clothes. You put it to keep warm. So so each scarf is a mixture of 2 colors. Okay, so you probably you choose I don't know, yellow and red. You choose 2 colors to make a scarf. And so there are several different kinds of scarves. But you are not. I'm not saying that you can choose any 2. So this depends on the taste of people and the people who decide to do it in this way or the other. So I'm saying that each scarf is a mixture. You choose 2 colors for it. Okay, but it's not. I don't know if color 1 and color 2 combine into some kind of scarf. Okay, I don't know that. So I'm saying that each color is used to pair other colors, at least 3 of them. So let's say, suppose each color is used to pair at least 3 other colors. Okay. Then prove that prove the following. We can choose 3 scarves which contain exactly 6 colors. Okay, so I have the feeling that sometimes in a Olympiad contest problem, it's a little more awkward to it contains a lot of words, but it's sometimes I feel simpler if you translate it into a graph theory. So what is going on? So I want to take a graph on 6 vertices, representing exactly these 6 colors. Okay, so if you find some actual scarf making made of 2 colors, for example, the first color, second color, then you just drawing an edge. Drawing an edge between, say, VI, VJ. If the color IJ, the color VI, VJ representing exactly 2 colors, okay? So if the colors VI, VJ are used to make a scarf, okay, then we got a graph on 6 vertices. So what is the condition here? It says that each color is used to pair at least 3 other colors. So it translates to the degree of Vi for each I is greater or equal than 3 for each I. So you have a graph on 6 vertices, and every vertex has degree at least 3, which is half of 6. Okay, so now this satisfies the condition of Dirac. By Dirac's theorem, we find what? So G, so the graph G has a Hamiltonian cycle. Hamilton cycle. So it contains a Hamilton cycle. Let's say V1, V2, V3, V4, V5, okay, V6, and then we are back to V1. So this is a Hamilton cycle. So in particular, we see that V1, V2 is an edge, V3, V4 is an edge, and then V5, V6 is an edge. So this is a scarf, this is scarf, this is scarf. We find 3 scarves with exactly 6 colors. Okay, what is this? This is a matching, okay? This is what we call a matching. I don't know if I have introduced this, but it's very easy to introduce. So if you have a graph with even number of vertices, and you see a structure like this. So you have, for example, 2n. So the number of vertices is 2k, for example. N equals 2k. And if you find the k edges like this, and clearly it covers all the vertices, we call this a matching. In fact, if it covers all the vertices, we call it a perfect matching. A matching is just such a structure, okay? If it covers all the vertices, we call it perfect. So this 3 graphs with exactly 6 colors, this thing is a perfect matching. Okay? It's just a problem. All right. Okay. So I think I'm going to so before the interval, before we take a break, I think I'm going to introduce a more advanced technique, which I will not prove it. It's very useful because I'm doing some random graph stuff right now. I mean, in my research. So I found that this seemingly more advanced technique is actually related to the proof you just seen. I will not give a full. So I think I'll take 10 minutes to talk about this optional stuff, which is called Posas rotation. It's very beautiful. I think it's very clever. So given a graph, given a path actually, given a path in a graph, I want to do this because it's more advanced. So I'm not going to give proof. I want to do this because it's really related to this thing. Okay, I think it's inspired by. It was inspired by this argument I just presented. So a path in a graph, let's call V1 again. Okay, so until Vk, okay? And probably we have Vi here and Vi plus 1 here. So it's a path. And suppose that Vi, Vk is an edge. So here you see an actual edge. So it's a path, but with an actual edge. So this rotation, this so-called rotation, is the following. So we perform the following. So first we delete Vi plus 1. So remember here we also delete the same word edge. You see, in the end of this proof, we deleted this edge to get a Hamilton cycle. So this kind of partially what we did before. It's half of what we just did. We delete Vi vi plus 1. And we see a path which is v1 until vi. And then we directly jump to vk. And then we follow this segment backward until vi plus 1. You see, this is a new path. So this path, if we call it p prime, so we kind of start from p, here is p, and we do this so-called Poisson rotation. After this Poisson rotation, we obtain a path p prime. So these two paths, they have the same vertex set. We didn't introduce other vertex, and we didn't delete any vertex. But the structure of the path changed. This path, for example, it finished at point vi plus 1. But the path p, it finished, the endpoint is vk. So okay, v1 is the endpoint of both paths. But vk is endpoint of p, and vi plus 1 becomes the endpoint of p prime. Right? Okay. So there is this is what we call Poisson's rotation. But what is really useful is the following Poisson's lemma, which I will not prove. Says the following. So if we start with p, okay, like I said, v1 until vk. I start with this path p, and we write p, which is curlied p, is a big p. Okay, p is denote as which we use it to denote a site, to represent a site. So is the site, right, to be the set of all possible paths obtained from P, from the original P, by performing several or a series, several finitely many times of this rotation. So you see, after we get this p prime, probably we decide to look at vi plus 1, maybe to connect some other vertex, and we perform this rotation again. So we are allowed to put this rotation finitely many times, and we obtain an abstract set of all the possible paths. We write it as p. Okay. So, and then what? Then we want to we define this x, okay, to be the set of all the end vertices of all the passes you see in P. Okay, the set of all ends. Let's just write ends and vertices of all the paths in P. Okay, it's a finite set. It's a subset of P. It's just eventually you get a subset of V1 until Vk. But I think it becomes fairly complicated. You don't know. You don't have a concrete example, and you define something, and you look like it reached pretty far. Okay. So the conclusion is very interesting. The conclusion is that if you look at inside P and you look at all the neighbors, let's write npx. Okay, so in this set p, maybe vp. Okay, maybe I write vp. I don't look at other vertices outside this path. I just look at the subgraph formed by these vertices. So this is actually a subset of which we call x minus union with x plus. So where x minus is the set of vertices which are right before x. X plus is the set of vertices that are right after x. So imagine if this is my, right before, right after in the original p. Okay, so it's a little complicated. So this is my p, v1. I don't know, v2, v3. I don't know how many vertices I should draw, vi. And eventually, probably I get vk minus 2, vk minus 1, and vk. Okay, so I'm saying that maybe this guy belongs to my x, because after some rotation, it becomes an endpoint. And maybe this guy is my point, a point of x. And for example, I only have, for sure, vk is in my in the set because it's original endpoint. Okay, v1 also. Okay, so suppose x only has exactly 4 vertices. Okay, so v1 in the original path p has no vertex on its left, so it's because it's leftist. Okay, v1 is on the far end point of in the left, so there is no other vertex on the to the left of it. Similarly, vk has no vertex to the right of it. Okay, so what is x minus? Probably is this point. So you have vi minus 1. This point you see vk minus 3. Okay, the left point of vk minus 2, and we have vk minus 1, which is the left point of vk. So x minus is this three vertices. And what is x plus? So this time you have v2, because v1 has a right point, and vi plus 1. Okay, the point after vi, and vk minus 1 again. You see, but vk, it has no right point. Okay, it has no right vertex. Okay, so this is the definition of x minus and x plus. So the conclusion says that the neighbor of x is contained in these two sets. Okay, so it's fairly complicated, but this control becomes very important. Okay, so in some computations, yeah, what happens is in reality, let's just make a final comment remark. So suppose we are trying to look for a Hamiltonian cycle, Hamilton cycle in some graph. We don't know if the graph admits Hamilton cycle, so we pick. So in order to find a Hamilton cycle, we pick. This is a very, very standard method. So we pick a so-called longest path, P, and then we write it down. So probably we write it as V1 until Vk. Okay, this is the longest path. Then we try to perform pulsar rotation and get the set X, for example, the set P, for example. So okay, we got P first. So all the possible resulting passes, and X are all the possible endpoints and the vertices. Okay, and what's good about this? So if some point Y belongs to X, it means that you have some P prime obtained by performing rotation several times to P. It will be something like I don't know. I cannot write even V1. So VI1, VI2, and so on. But it ends at the point Y. Okay. If Y is in X, by definition, you have some kind of mixed ordering, and then this is a path we call P prime, and this path ends with the point Y. Okay, what's good about this? So first of all, Y cannot join any other. For example, this is the remaining part of the graph. So this is G. We are saying that we put a longest path, but it does not, for example, for now, as far as we know, it does not exhaust all the vertices. So there is a possibility it has a remaining part. For example, here you have some vertex Z, which is not one of these vertices. So then Y cannot join Z. So YZ is non-edge. Because if Y joins Z, then we can extend this path to make it longer, but we choose the longest path in the first place. So if you can, for some reason, show that after post-association, this set is really large, then you find a really large set which does not join this set R. Okay, so we find a really large X. So what I'm saying that is that by this argument, the edge of X and R is 0. There is nothing. But sometimes this is not possible. If you put some condition on the graph, it's not possible, and then you get a contradiction. I've seen this kind of argument so many times in research papers, so I think I want to describe it to you. But it's a little more advanced. Okay, so that's it. I'm going to stop for some time. Let me finish the recording for the first part. Great. So let me start another page. So I think the first part is the most important thing I ask you to remember. And then if you understand the concept, there are several other things to discuss, but it's not so difficult, I think. So for example, if we work, for example, let's work with bipartite graph now. For example, G on a bipartition A and B. So it has two parts, A and B. Oh, here. Okay. So I'll be interested in if this graph has, for example, we have A and B. If this graph has for example, if G admits a Hamilton cycle, okay, so you can imagine you start from something like this and do this, and eventually it comes back. So I think it's very clear that both A and B must have the same size. Okay, and this is the conclusion. So it implies that A and B have the same size. For example, we have V1, V2, and you follow this until V2k. And here is, for example, V2k minus 1. So, right? So if G Further, if G, it does not have a Hamilton cycle, but it has a Hamilton path. Now, then let's say the difference of A and B is 1, -1, 0, or 1. So their size difference could be at most 1. Because if you have A and B, probably you have something like this. And then if you count, this A part has 1 more vertices than B. Or it can be the same, and all this is part A, this is part B. Or you can do something like this. So in this picture, you have 3 vertices in A and 4 vertices in B. Okay, so either A has 1 more vertices than B, or B has 1 more vertices than A, or they have the same size. So it's not possible that one part has 2 more vertices than the other part. Okay, so this observation is very simple, but you use it to solve some problems. For example, let's see another problem. So again, when you state this problem, you kind of you don't feel it's the same thing. Okay, but you have to translate. So let's look at a board. So a chess board. Okay, it has that's 1, 2, 3, 4, 5, 6, 7, and here, but here it's kind of has 1 more. I don't know if you have seen this kind of problems in Olympia contests. They kind of like this kind of problems. Here there is a knight. There is one knight here, and the question is it possible this knight move so each time cross the board to another small cube? Okay, so you can move like this, whatever, and is it possible to it starts here and moves every position and stops at some other place? Okay, so this is the question. So I don't think I need to write the question. The answer is no. Okay, so it's not possible to move the knight to go through every, let's say, position. Of course, are not allowed to repeat what you have been traveled. Okay, so how to solve this? So you have to be a little clever. So you need to shade the board, say, in this way. So this board is shaded. Okay, so you realize that by rule, sorry, have this guy, not this. By rule, each time you can only move from a shaded to an unshaded position, or to a white unshaded position to a shaded position. So let me say, so each step, you can either move from a shaded position to a unshaded position, or vice versa. Or from unshaded position or shaded position. So it means if I put all the shaded position as part A and all the unshaded position as part P, I just put the numbers V1, V2, okay, in all these positions. And I gather all the shaded here and unshaded here. And if you are allowed to move from here to here, you draw an edge here. Is this description clear? And I got a bipartite graph. And what I asked in this question is find, so this problem reduces to finding a Hamilton path. Okay, so if you count, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this shaded part, the shaded part has 14 vertices, and this unshaded part has 12 positions, 12 vertices. So in particular, because their difference is 2, so in particular, there is no Hamilton path. Okay, so that's the problem. All right, so there are some variants of this kind of problems. In your lists this week, I will put at least one problem of the same flavor. Okay, you have to you are required to define a graph to understand the problem. Once you understand the problem and you apply these things about these properties of Hamilton paths or cycles, you will arrive at a conclusion. So let's come back to the proof of Oz theorem, which is the central part of today, like I said. So let's make a little more definition and deeper dig a little deeper. So recall in Oz theorem, the proof. Recall its proof. So remember what we did is that we draw something like this, and which is the minimal kind of maximum example, and then we say that okay, V1 degree and the Vn degree, the degree sum is greater or equal than, and then we must find two vertices, and we see this. Okay, remember this proof. So okay, the proof, the starting of the proof is that V1 Vn has no edge. Okay, so in fact, if you think a little more carefully, the whole proof shows the following: if uv is a non-edge, and du plus dv is greater or equal than n. We used this condition to find this picture, remember? So if first, this is a non-edge, and the degree sum of the two vertices is at least n. If this is satisfied, then so G is Hamiltonian if and only if G plus UV is Hamiltonian. Okay, so this I'm not leaving it, but it's really an exercise. So what's happening is that remember how I explained. I didn't write it. I explained how we arrive at the extreme example. Okay, so if G is not Hamiltonian, and we found if there is a path like this and an edge, you can just add it. It cannot be a Hamiltonian also. So you have to think about this. It's not for free, but in the proof, you have this. So, I mean, after this observation, people make further definitions. So this is also useful in the understanding of Hamilton passes. Further definition. So Hamilton closure of a graph G denoted by C of G. So you have a graph G, and we will define another graph which we call C of G. Sometimes people say it's closure of G, but it's actually Hamilton closure of G. It's obtained denoted by C of G is the graph obtained from G by keep adding edges like this. So by adding edges UV with du plus dv greater or equal than until there are no such non-edges. Okay, so to make this definition makes the helps to understand the property of Hamiltonian a little better. So we have this theorem, which is not very difficult to prove. A simple graph G admits Hamilton cycle if and only if its closure admits Hamilton cycle. Okay, so basically it's like every step, if you add an edge, you obtain a new graph. The original graph, if it has Hamilton cycle, the new graph also. And eventually the closure, if you do this as many times as possible, eventually you arrive at the closure. This closure, C of G, also admits Hamilton cycle. Okay. So the proof of the theorem is a little strange because essentially what you want to do is that to check closure is well defined. Because of this observation, the remaining of the proof is kind of trivial. So we only need to check that the closure C of G is well defined. So in mathematics, sometimes you define something. There's a possibility that the object you define, in this case, C of G, is not well defined. What does it mean? It means that, look, because definition is fairly complicated, if I find a non-edge satisfying this property, I add it. And then I look at the graph. I find another edge, a non-edge, which satisfies this property. I add it again until there is no such non-edges. I stop. But if you do it instead of me, you probably you choose different orders. Probably you choose some other non-edge first. So it seems not sure that we arrive at the same graph. This is what we have to check. We have to check that eventually we are arriving the same graph. And this graph we call CZ is therefore well defined. Okay, so this is the thing. So this is why we say we have to check this graph is well defined. So in order to do this, suppose we see two processes. So from G we add E1, E2 until say EK to obtain G1. And also the same graph G as F1, F2 until FL to obtain G2. So we want to track G1 and G2. Okay, I say to obtain G1 means that there is no other non-edge which has satisfied that property anymore. G2 also. So we need G1 is G2. So we only need we need to track only G1 is a subset of a subgraph of G2. Because looking at the definition, there is no difference. If you can prove that G1 is subset of G2, G2 is also subset of G1. Okay. So we only need to check that G1 is actually a subset of a subgraph of G2, and that's it. So to prove this, so let's say we put a observation. Observe that. So if and any time of the whole process, if UV is a non-edge, okay, at any point of the process, I mean the whole process, adding edges. If we find a non-edge UV, and their degree sum is greater or equal than n. Okay, so it means eventually this UV will be added. Okay, do you agree? Because maybe this time we didn't consider this non-edge, but next time, since their edge degree sum is already greater or equal than n, maybe you are busy with other non-edges, but after you add some other edges, this sum could be even larger. But eventually, if you are not stopping, meaning that you still can find some non-edge satisfying this property, this non-edge is waiting there. So eventually you have to add it at some point. So using this observation, let's start with E1, say. So E1 here can be added to G this fact means that both ends, so the degree sum of ends of E1 is greater or equal than n. Because this is the first edge to be added. It must satisfy this property. So the degree sum of this edge is at least n. So by this observation, E1 must equal to some Fi for some I. Okay? I mean, during this whole process, there must be some I. Fi is exactly E1. And by induction, let's suppose, I put an induction hypothesis that E1, E2 until EK minus 1 are already added. Then I want to look at EK. Okay, this is EK minus 1. I look at EK. Look at the non-edge EK at this point. Because in this order, K is not the last one. Let me say EJ minus 1. I look at EJ. Okay. So at this point, by this order, since I can add EJ, it means that the degree sum of ends of EJ is greater or equal than N. Because otherwise I cannot add it. There is an order here. I put all the E1, E2 until J minus 1. Then the next edge I want to add is EJ. I can add it because at that point, the degree sum of two ends of EJ must be greater or equal than N. But now, by the observation, I know that EJ must equal to some I, for example, I, for some I. Okay? So this observation, let's record this. So if this non-edge satisfies this, then it means eventually it will be added. If you look at the second process. Then by induction, every EI is one of Fi. Actually, one of EJ is one of Fi. So it means that E1 is a subset of E2. And if you look at the other way, you start from F1 and F2 inductively, you can prove that every Fi is also one of EJ. So actually, these two sets of edges must be the same set. Okay, that's the thing. Okay, it's not entirely obvious, but we have proved it. Okay. So only this. I think we are kind of early today, so we finish all I planned. So there is some other big theorems. Maybe I'll state it. So it's kind of a big theorem by Erdős again. So there is more properties to describe it. Let me see. Okay, it's only one paragraph. I think I will leave you to read it by yourself. It's the last page of the notes I'll send today. Okay, so I think I finished earlier today. So it's only here until here. Any questions? Okay, so so that's it. So let me finish the recording. Stop recording.